It is completely wild to think about, but just a century ago, gardening was essentially an extreme sport.
It really was. I mean, a simple scratch from a rose bush or, a blister from a stiff new pair of shoes.
Could literally be a death sentence. You get a little dirt in a cut, the area gets red, streaks start traveling up your arm, and, well, that was it. Game over. You just hope your affairs are in order.
Right. There was absolutely no safety net. Human beings lived entirely at the mercy of microscopic organisms. We were losing a massive invisible war that we didn't even fully understand yet.
But then we found the ultimate safety net, right? Antibiotics. And because they worked so miraculously well, we basically immediately started taking them for granted. Which brings us to our mission today. We are taking a deep dive into the fascinating high-stakes world of these life-saving drugs.
Yeah, and we're going to look at them specifically through the lens of the people on the front lines of healthcare. So, nurses, clinical pharmacists, the people actually administering these medications to you.
Exactly. We need to understand how these drugs actually hunt down bacteria, why the safety net is suddenly fraying, and why that golden rule you grew up with, always finish your prescription, is suddenly at the center of a massive medical debate.
Yeah, because the era of just casually throwing a Z-Pack at every sniffle, that era is rapidly closing.
Okay, let's unpack this. Before we get into the looming crisis, we really need to figure out what an antibiotic actually is. And from what I understand from our sources, the definition itself is a bit of a moving target.
It has shifted quite a bit, actually. Originally, an antibiotic was strictly defined as a weapon used in microbial warfare.
Microbial warfare?
Yeah. So it had to be a natural compound made by one living microbe to kill another living microbe. Think of like a mold in the soil fighting off a nearby bacterium for resources.
Right. So under that strict old-school definition, if a scientist creates a germ-killing drug entirely from scratch in a chemistry lab, it's not technically an antibiotic.
Precisely. Historically, strict pharmacology textbooks would insist that fully synthetic drugs were antimicrobials or antibacterials, but not antibiotics. But in modern clinical and nursing fields, the term has completely broadened.
Oh, okay.
Today, it essentially means any drug used to treat a bacterial infection inside the body, whether it was found in a damp forest or, built molecule by molecule in a lab.
Good to know. So we don't get tripped up by old textbook definitions if we're reading the literature. Now, the story of how we actually found these things, it is full of drama. When you read the history, it's not just neat scientists in pristine white coats having quiet eureka moments. It's a lot of dirty petri dishes, massive egos, and stolen credit.
The ego and sheer stubbornness that drove these early discoveries is incredible. Take Paul Ehrlich in the early 1900s. He established this revolutionary concept of the magic bullet.
Magic bullets.
Right, the idea that you could find a chemical to selectively kill a pathogen without killing the patient. He's trying to cure syphilis, and he systematically screened hundreds of toxic arsenic-based compounds.
With arsenic, the thing famous for, poisoning people.
Exactly. And it wasn't until the 606th compound that his team found one that worked without immediately killing the host.
Wow.
It was marketed as salvarsan in 1910. He actually coined the word chemotherapy for this, though back then it just meant the chemical treatment of any infection long before it became synonymous with cancer.
606 tries. That is a level of persistence I just cannot fathom. But then there's the story that sounds like it was written for a Hollywood movie, Gerhard Domack, in 1932.
Yes, Domack. He was a German pathologist working for a chemical company, and he discovers that a synthetic red dye called Prontosil protected lab mice from lethal streptococcal infections.
A red dye.
Yeah, but the real drama happened when his own daughter, Hildegard, developed a life-threatening infection.
From a sewing needle prick, right. Just like the rosebush scratch. And he's a scientist watching his daughter actively dying, and he takes this massive gamble to give her this experimental industrial red dye.
And it saves her life.
Unbelievable.
The human body actually metabolizes Prontosil into a compound called sulfanilamide, making it the ancestor of all the sulfa drugs we use today. Domack won the Nobel Prize in 1939 for this, but the story takes a really dark turn. Nazi Germany actually forced him to decline it.
Wait, really?
Yeah, he was arrested by the Gestapo for a week just for being awarded the prize. He didn't receive his actual medal until 1947, long after the war.
That is wild. A literal miracle cure wrapped up in global fascism. But when most people think antibiotic origin story, they immediately think of a very messy desk in London.
Right, Alexander Fleming in 1928. He goes on a summer holiday, leaves his laboratory petri dishes out, and comes back to find a mold. Penicillium notatum had contaminated a dish of Staphylococcus bacteria.
Just left it out.
Yep. But what he noticed was a clear halo, a ring around the mold where the bacteria had been completely wiped out.
The ultimate task failed successfully moment in human history.
It really was. Though it's worth noting, Fleming couldn't actually purify it into a usable drug himself. It took a brilliant team at Oxford, Howard Florey, Ernst Boris Chain, and Norman Heatley to figure out the incredibly fragile chemistry and scale up penicillin to make it a functional medicine during World War II.
And then we have Selman Waksman, who actually coined the modern word antibiotic in 1941. He was systematically screening soil bacteria looking for these chemical weapons.
Yes, and this is where the dark side of academic credit really rears its head. Waksman's graduate student, a man named Albert Schatz, was the one who actually isolated streptomycin in a basement lab in 1943.
Which was a big deal.
A huge deal. It was the first drug that could cure tuberculosis, a massive world-changing discovery. But Waksman took all the credit and eventually the Nobel Prize, entirely alone.
Ouch. I mean, as a grad student, doing the literal dirty work in a basement to watch your boss take the Nobel for your discovery, that is brutal.
Schatz actually did the unthinkable for the time. He sued his mentor.
Oh, wow.
He sued Waksman in Rutgers University. He won formal recognition as a co-discoverer and a share of the patent royalties, but he was essentially blacklisted in the academic community for speaking up. It remains a classic cautionary tale that historians point to about power dynamics in science.
So we have this arsenal of miracle compounds born from arsenic, red dye, moldy dishes, and bitter lawsuits. But here is the fundamental question. You mentioned Ehrlich's magic bullet. If these drugs are essentially microscopic poisons designed to violently kill living cells, why don't they kill our cells when we swallow them?
That is the absolute cornerstone of pharmacology. It's a concept called selective toxicity.
Selective toxicity, meaning it's toxic, but only to a select target.
Exactly. To work safely, the drug has to exploit a specific structural or biochemical difference between a bacterial cell, which is a simple organism called a prokaryote, and a human cell, which is a more complex eukaryote.
Right.
If the drug can find a biological target that the bacteria absolutely relies on, but that human cells don't even possess, it can slaughter the invader while leaving the human host completely unharmed.
So it's like targeting the exhaust port on the Death Star. You are finding the one architectural flaw the enemy has that we don't, and dropping the torpedo right there.
That is a brilliant analogy. And for nursing education and clinical practice, organizing these drugs by which specific exhaust port they target is the fastest way to understand how they work, predict their side effects, and manage drug interactions.
Instead of just memorizing a list.
Exactly. Instead of just memorizing complicated names, you look at the spatial journey into the bacterial cell.
Yeah.
There are 5 major mechanisms or buckets we need to explore.
Okay, let's take that journey. If I'm an antibiotic attacking a bacteria, the first thing I hit is the outer defenses, the deflector shield.
Precisely. That's our first bucket cell wall synthesis inhibitors. Bacteria have a rigid outer wall made of a highly cross-linked substance called peptidoglycan. It's like a heavy suit of armor.
And human cells don't have that.
Nope. Human cells do not have this wall at all. We just have a soft membrane.
So how do the drugs break the armor?
They don't just break it. They stop the bacteria from maintaining it. Penicillins, for example, have a specific chemical structure called a beta-lactam ring. This ring perfectly mimics the natural building blocks the bacteria uses to build its wall.
Oh, sneaky.
Very. When the bacteria's enzymes grab the drug thinking it's a brick, the drug jams the enzyme permanently.
Wow. So the bacteria is trying to build its wall with fake bricks, the machinery jams, and then what? Does it just sit there?
No, it dies violently.
Yeah.
Bacterial cells are highly pressurized on the inside. Without that rigid wall holding everything together, the bacterial cell literally bursts open under its own internal osmotic pressure.
It just pops like an overinflated balloon.
Exactly. This is the largest, most clinically important group of drugs. It includes the penicillins, it includes cephalosporins, which are organized into generations.
Wait, generations? Like an older and newer version?
Yes. As you move from first to second to third generation, the drugs trade their ability to kill gram-positive bacteria, which have very thick outer walls, for the ability to kill gram-negative bacteria.
What's the difference?
Gram-negative bacteria have a thinner wall, but they have an extra sneaky outer lipid membrane that makes them incredibly hard to penetrate. The newer generations were designed to slip past that extra membrane.
Ah, so it's upgrading the torpedo to pierce different types of shielding? What else is in this first bucket?
You have carbapenems, which are incredibly broad-spectrum, heavy hitters.
Yeah.
These are often locked away in the pharmacy, reserved as the absolute last-line therapy for severe hospital infections to prevent resistance.
The big guns.
Right. Then you have monobactams, which are crucial because their chemical ring doesn't trigger allergic cross-reactions, making them safe for patients with a true severe penicillin allergy. And finally, glycopeptides, like vancomycin, which is chemically different but attacks the same wall. Historically, that's our last resort against superbugs like MRSA.
Okay, so bucket 1 pops the deflector shield. Let's say the bacteria doesn't have a thick wall or we need to attack it differently. We breach the perimeter and go for the inner lining.
That brings us to bucket 2 cell membrane disruptors. Instead of stopping a wall from being built, these drugs, like the polymyxins, act almost like detergents. They punch physical holes directly into the existing bacterial cell membrane. The cell leaks its vital contents and dies.
I have to stop you there. If human cells also have membranes, you said earlier we have soft membranes instead of walls, wouldn't a drug that punches holes in membranes punch holes in our cells too? Isn't that friendly fire?
You've hit the nail on the head. That is exactly why selective toxicity isn't always perfect. Polymyxins are older drugs, and they are quite toxic to human kidneys and the nervous system.
So why on earth do we still use them?
Because they've been revived recently out of sheer desperation. For some superbugs that resist every single wall-destroying drug we have, especially those carbapenem-resistant organisms, these highly toxic hole punchers are literally the only things left that work.
That is terrifying. Okay, moving deeper into the cell. We've bypassed the wall and the membrane. Now we're inside the bacteria. What's the next target? Bucket 3.
The internal droid factories. Protein synthesis inhibitors. Bacteria need to constantly manufacture proteins to survive, just like we do. They use cellular assembly lines called ribosomes. But bacterial ribosomes, called the 7DS ribosome, are structurally different from human ribosomes, which are ADS.
Hold on, 70S, 80S. You lost me. What does that actually mean and why should I care?
Oh, the S just stands for Svedberg units. It's a matter of how heavy and dense the molecule is. All you really need to know is that the bacterial factory is physically a different shape and size than the human factory.
Okay, that makes sense.
Because of that structural difference, these drugs can slip inside the bacteria and throw a wrench directly into the gears of the 7DS ribosome, completely halting bacterial protein production, while our ADS human factories keep chugging along right next door.
That is incredibly elegant. So what drugs are we talking about here?
Several major ones. Aminoglycosides are here. They are powerful against gram-negative bacteria, but require nurses to monitor drug levels in the blood closely because they can cause severe kidney and ear toxicity. You also have tetracyclines. These are fascinating mechanically because they strongly chelate or bind to calcium.
Calcium, like in our bones.
Exactly.
Yeah.
That's the primary reason we avoid giving tetracyclines to children or pregnant women. The drug binds to the calcium in developing teeth and can permanently stain them gray or brown, and it can even temporarily stunt bone growth.
That is a side effect you definitely want to remember if you're a nurse handing out pills.
Yeah.
What else jams the ribosomes?
It's macrolides. If you've ever had a respiratory infection and been handed a Z-Pack that's azithromycin, it has a long half-life in the body, which is why you only need a short 5-day course. This group also includes lincosamides like clindamycin, which has a notorious reputation we'll get to in a minute, and oxazolidinones, which are newer drugs used for deeply resistant superbugs like MRSA and VRE.
All right, so we've jammed the factories. What if we want to go straight for the central computer, the blueprints?
That's bucket 4. Nucleic acid synthesis inhibitors. These target the enzymes bacteria use to uncoil and copy their DNA and RNA. If they can't copy their DNA, they can't multiply. Fluoroquinolones, like Cipro, live here. They are highly effective, but they carry heavy FDA-boxed warnings.
Warnings for what?
They can cause spontaneous tendon rupture, like your Achilles tendon just snapping, and even aortic aneurysms in rare cases.
Tendon rupture from taking an antibiotic for a UTI, that is completely wild.
Yeah, it's a stark reminder that these are potent systemic chemicals, not candy. Another fascinating drug in this DNA blocking group are the rifamycins, used heavily for tuberculosis. And here's a critical clinical pearl. They block bacterial RNA polymerase, but a hallmark side effect is that they turn bodily fluids, urine, sweat, and even tears a bright orange-red color.
Oh my God. Nurse, why am I crying orange tears? Yeah, a heads up would be nice there.
Exactly. Nurses have to proactively educate patients about this, or the patient will think they are sweating blood and go into sheer panic.
Okay, that brings us to the final mechanism. Bucket 5. We've hit the wall, the membrane, the factories, and the blueprints. What's left?
The supply lines. Metabolic pathway inhibitors. These drugs block specific steps in how bacteria process essential nutrients. The classic example is folic acid. Bacteria need folic acid to synthesize their DNA. Sulfonamides and trimethoprim block the specific enzymes bacteria use to manufacture folic acid from scratch.
But wait, human cells need folic acid too, right? My pregnant sister takes a folic acid supplement every day.
We absolutely need it. But human cells don't have the metabolic machinery to synthesize it. We have to get it externally from our diet or vitamins. Since we don't have the factory to make it, targeting that factory in bacteria is a textbook example of selective toxicity. They often combine two of these drugs, like in the medication Bactrim, to block two different steps in the bacteria's supply line at the exact same time. It's incredibly effective.
Okay, so we have these incredibly precise tools. We've got torpedoes for the wall, the protein factories, the DNA, the membrane, and the metabolism. But I have to push back here, or at least play devil's advocate for you listening.
Go for it.
If I'm really, really sick, I have a high fever, I feel terrible, why wouldn't I just want the doctor to prescribe the absolute strongest broad-spectrum antibiotic they have in the pharmacy? Just wipe everything out. Nuke it from orbit.
That is a very common and very dangerous misconception. People hear the term broad spectrum and think it means more potent or stronger. It doesn't. A broad-spectrum drug doesn't kill a specific bacterium any harder. It simply means the drug is chemically capable of attacking many different types of organisms at once.
And why is that a bad thing? If I don't know exactly what's making me sick, shouldn't I just cover all my bases?
Because of the friendly fire you mentioned earlier, your body is home to trillions of protective normal flora. The good bacteria living on your skin, in your mouth, and especially in your gut. They take up space and resources so harmful, invading pathogens can't move in and set up shop.
Ah, I see where this is going. If I use a broad-spectrum drug unnecessarily, I'm basically carpet bombing my own internal defenses.
Exactly. You are wiping out the peacekeepers.
Oh.
And that collateral damage leaves you wide open for what we call superinfections. The most classic terrifying example in healthcare is Clostridioides difficile or C. diff colitis.
Which you mentioned earlier is heavily associated with clindamycin.
Yes, as well as fluoroquinolones and broad-spectrum cephalosporins. When you wipe out the normal, healthy gut bacteria, this one toxin-producing, highly antibiotic-resistant organism, C. diff, survives the blast. With no competition left, it rapidly takes over the entire colon. It causes severe, sometimes fatal diarrhea that is incredibly difficult to cure. So a narrower, targeted therapy, a sniper rifle instead of a grenade, is always preferred the moment you know exactly what specific pathogen you're fighting.
You want the sniper rifle. And while we're talking about massive misconceptions, let's clear up the biggest one. Viruses. If I have a terrible viral flu or the common cold, why won't a doctor give me a Z-Pack?
Because antibiotics do not work on viruses, period. Look at the mechanisms we just discussed. Viruses do not have a peptidoglycan cell wall. They do not have bacterial 70S ribosomes.
You can't target an exhaust port that isn't there.
Exactly. Taking an antibiotic for a viral infection does absolutely nothing to the virus, but it still detonates that grenade in your gut. It wipes out your good flora, exposes the surviving bacteria to selective pressure, and contributes to global drug resistance for zero benefit to you.
Which actually brings us to a massive contradiction. We just talked about minimizing collateral damage, minimizing exposure. Yet for my entire life, every doctor and nurse told me the golden rule. Never, ever stop taking your antibiotics until the bottle is completely empty, even if you feel 100% better on day 3. Doesn't taking them for 14 days cause more collateral damage than taking them for 5?
Here's where it gets really interesting. That dogma, the absolute holy grail of 20th century medicine, is being actively dismantled.
Wait, really? So stopping early doesn't create superbugs?
It's much more nuanced than we were taught. In 2017, a group of infectious disease experts, led by Martin Llewellyn, published a highly provocative paper in the BMJ arguing that the finish the course dogma was never actually supported by rigorous scientific evidence.
Yeah.
We literally just made up the durations, like 10 or 14 days,
Yeah.
because they were nice round numbers.
So what does cause the resistance, if not stopping early?
Their central point is that resistance is driven by total drug exposure. Think about it. When you take a long 14-day course, by day 12 or 13, the drug levels in your body are tapering off. You are exposing the surviving bacteria to low, sublethal concentrations of the drug for an extended period.
Oh, wow. So by taking more of the drug longer than I actually need to cure the infection, I'm essentially giving the surviving bacteria a low-stress training camp to figure out how to beat the drug.
Exactly. The longer the exposure, the higher the chance of selecting for resistant strains. Now, to be incredibly clear, the takeaway from modern research is not just stop taking your medicine whenever you feel like it.
All right, we don't want anyone listening to just start freestyling their medical care based on a vibe. I feel great today. Into the trash they go.
Please do not do that. Critics of the BMJ paper rightly pointed out that for serious, deep-seated infections like tuberculosis or endocarditis, which is an infection of the heart valve stopping early, is well documented to cause a deadly relapse. The expert consensus today is about precision. Course lengths need to be entirely evidence-based for the specific infection.
So why finishing the course still matters is because the course itself is changing.
Precisely. We now have clinical trials proving a 3-day course works reliably for an uncomplicated UTI, and 5 days is often plenty for community-acquired pneumonia. If your doctor prescribes 5 days based on the latest evidence, you absolutely must finish those 5 days. But we no longer need to blindly prescribe a 14-day supply for everything just because a textbook from 1980 said so.
But getting this right, matching the exact drug and the exact duration to the exact bug, it feels so urgent because this resistance crisis isn't some abstract sci-fi problem for the year 2100. It's happening terrifyingly fast.
It is immediate, and it's been happening since the beginning. Let's look at methicillin. It was a synthesized penicillin introduced in 1959, specifically because staph bacteria had already figured out how to chew up regular penicillin. Just 2 years later, in 1961, doctors in the UK identified the very first strain of MRSA, methicillin-resistant Staphylococcus aureus.
2 years. It took humanity thousands of years to find the drug, and it took a microscopic blob 2 years to completely outsmart it.
2 years. It is the clearest possible demonstration that resistance isn't a mistake. It is the built-in evolutionary consequence of using antibiotics at all. Alexander Fleming himself anticipated this. In his 1945 Nobel lecture, he explicitly warned that underdosing penicillin would cause resistant bacteria to survive and multiply. He predicted the crisis before resistance was even a widespread clinical problem.
And now because we didn't listen, we have things like NDM1.
Yes. New Delhi metallo-beta-lactams 1.
Sure.
First described in 2008. It is a resistance enzyme that completely destroys carbapenems.
Wait, carbapenems, the ones you said were locked in the pharmacy as our absolute last resort. Bucket one.
Exactly. NDM1 neutralizes our last line of defense. But the true nightmare scenario isn't just that a single strain of bacteria mutated to have this enzyme. It's how they spread it.
What do you mean spread it? They don't just divide and pass it to their offspring.
That's vertical transmission. But bacteria can also do something called horizontal gene transfer. The genetic code for NDM1 sits on something called a plasmid. A plasmid is a small, mobile, circular piece of DNA that exists completely separate from the bacteria's main chromosome.
Like a little USB drive of genetic code.
That is exactly what it is. And bacteria can literally trade these USB drives with each other across totally different species. Resistance doesn't just spread when a bacterium reproduces. A completely unrelated bacterial species, say an E. coli in your gut, can bump into a Klebsiella bacteria and just hand over the plasmid.
Like swapping trading cards. Here, take this gene that makes you invincible to the strongest drug humanity has. Thanks, here's one for surviving tetracycline.
Exactly. They build multi-drug resistance shields in real time across species lines.
So what does this all mean for you, for the people listening? We are looking at a landscape where the World Health Organization has repeatedly warned that we are heading toward a post-antibiotic era. An era where common infections, routine surgeries, chemotherapy, even premature birth become deadly again, simply because the base assumption of modern medicine that there will be a drug that works is gone.
That is what makes antimicrobial stewardship the single most critical frontline job in healthcare today. Choosing the right drug, the sniper rifle at the right dose, for the exact evidence-based duration. It isn't just hospital paperwork. It is the only thing keeping modern medicine viable. Every time a nurse pushes for a culture before starting broad-spectrum therapy, or questions an unnecessarily long prescription, or educates a patient on why they aren't getting a Z-Pack for a cold, well, they are actively defending the safety net of humanity.
It really puts the responsibility on all of us, doctors, nurses, and patients, to respect these molecular tools. We can't just demand pills for a runny nose.
We can't. But I want to leave you with one final thought today, something to really explore on your own that builds on everything we've just discussed about how resistance forms. We've spent this entire deep dive talking about human medicine. Hospitals, prescriptions, nursing, fighting over a 5-day versus a 14-day course. But historically, a massive share of all antibiotics manufactured globally hasn't gone to sick humans at all. They are fed, by the ton, to completely healthy livestock.
Wait, healthy animals? Why would they give expensive drugs to animals that aren't even sick?
Because the agricultural industry realized decades ago that continuous low doses of antibiotics make animals gain weight faster, likely by altering their gut microbiomes to absorb more calories. Now, think about what we just discussed. If the major driver of antibiotic resistance isn't stopping early, but rather total drug exposure at long, sublethal concentrations, think about the
Oh
implication.
my God, the training camps.
Exactly. We have an invisible, massive pipeline of resistance genes and plasmids brewing in agricultural feedlots around the world. These invincible bugs are quietly multiplying in the soil, the water runoff, and entering the human food chain long before a patient ever even sets foot in a hospital to ask for a prescription.
That is profoundly chilling. Suddenly, the idea of a simple scratch from a rosebush being a death sentence doesn't just feel like a quaint history lesson from 100 years ago. It feels like a very real reality we could be facing again tomorrow if we're not incredibly careful about how we use these tools. Thank you for joining us on this deep dive. Respect your microbes, think twice about that Z-Pack, and we'll see you next time.